Howdy. I'd like to review a little bit of what we did in class today and then finish up with the discussion of special functions. We talked today about the properties of definite integrals. We divided those properties up into three categories. First of all, we talked about ways to simplify. And that included a sum rule. The integral of a sum, f plus g, is the same as the sum of the integrals of f and g. And likewise, we had a constant multiple rule, that the integral of a constant times f of x is the same as constant times the integral. And we walked through why both of these are true. It is because a definite integral can always be written as the limit of a Riemann sum. From this, we can immediately get a difference rule. The integral of a difference, f minus g, is the difference of integrals. So those were our simplification rules, and they allowed us to pull integrals apart and make them simpler before evaluating them. Then we talked about special interval rules. And we noted, first of all, the additive interval property. And the idea here is that if I integrate from a to c, f of x dx, and then I integrate the exact same thing from c to b of f of x dx, then what I'm doing is really just integrating the entire thing into pieces, so that if I integrate from a to c, the end point of my first interval matches the beginning point of my second interval right here, then I can just collapse all of that into a single integral, the integral from a to b of f of x dx. And this works both ways. So if I have an integral from a to b and I need to split it up into two pieces for some reason, then I can use the additive interval property to do that. The caution that I gave to you is to make sure that your two intervals are exactly adjoining each other. I have to go from A to C and then directly from C to B. So for example, I could not rewrite something like this with the additive interval property, and I also cannot do anything with different integrands. These two, well, the bottom one can't be simplified at all, and the top one would need to be rewritten in order to simplify. In addition to the additive interval property, we also consider the zero width property. And that is that if I integrate a function from a to a, here's my function, I'm going to integrate from a to a, then I am enclosing exactly no area whatsoever, so that I can immediately write that the integral from a to a of f of x is equal to 0, no matter what function f may happen to be. And then finally, we considered reversing the interval of integration. If I integrate from a to b, then what I am doing is taking and finding the net signed area under the curve as I travel from A to B like so. But if I reverse this and integrate from B to A, now I am going to be traversing the interval from A back to B in the opposite direction. And the only way to do that is to take the opposite sign for dx there, so that I end up with the opposite value for the integral. Practically speaking, this means that when we flip the limits of integration, we reverse the sign of the integral. All three of these properties are justified on the basis of picture. You can see that we are adding up from A to C to B gives us the same as adding up from A to B. You can see that if you go from A to A, then I am enclosing no width. And you can see that if I integrate backwards, then I'm going to end up reversing the sign because I must take a negative dx to do that. If these properties are confusing to you, then let the pictures guide. Now I want to consider special functions. And the first special function that I want to consider is going to be a constant function. So this would be a constant rule for definite integrals. If I integrate a constant function from A to B, then what I am doing is finding the net signed area under the curve y equals c from A to B, and that gives us a special shape, which is a rectangle, and as a result, that integral is going to have the value of the height c times the width b minus a. B minus a is here, and c is right there. We also began to consider what happens if we have an odd function or we have an even function. Now let me remind you of some definitions. An odd function is a function such that when you plug in negative x, what you get is the opposite of f of x. And I asked you to consider what happens when you integrate such an odd function from negative a up to positive a. And just to make sure that we're clear on what this would look like, remember that because an odd function is odd, then it is going to have origin symmetry. So if its graph looks like this in quadrant 3 here, then its graph is going to come out and look like this. It's going to be symmetric about the origin. I drew that kind of badly. But the point here is that any point x comma y on the graph here will have a matching point negative x, negative y on the graph over here. So if I take my odd function now and I add up net signed area from negative a to positive a, then all of the net signed area over here is going to be equal but opposite to all the net signed area over here. They will cancel each other out. And as a result, when I add up an odd function from negative a to a, I get 0. That's really helpful. So here's an example of this. Consider this integral, the integral from negative 1 to 1 sine of x cubed dx. Your first thought is, I don't know anything about sine of x cubed, and that's not a particularly special shape, so I can't find the value of this integral. Not so. Pay close attention to the fact that we are integrating at matching points from negative a to a. And pay close attention to the fact that both x cubed, the inside function, and sine of x, the outside function, are both odd. So let's do a quick check to see whether or not we are integrating an odd function by plugging in negative x to the integrand. And of course, the sine of the opposite of x quantity cubed is the same as the sine of the opposite of x, the opposite of x cubed. And because sine is odd, it is therefore equal to the opposite of sine x cubed. We have an odd function. And because we have an odd function, and we are integrating from negative 1 to 1, matching opposite points, therefore this integral has the value of 0 automatically. Even functions also have a nice property, although it's not quite as convenient. Recall that an even function has the property that when you plug in f of negative x, you get the same value as f of x. So here is an example of an even function. It shows y-axis symmetry because every point x comma y over here is matched by a point negative x comma y over here. So what happens if I integrate an even function from negative a to positive a? Well, the areas here don't cancel each other out. However, they are both equal to each other. So that I can write this even function property that the integral of an even function from negative a to a of f of x dx is simply going to be twice the integral from 0 to a of f of x dx. And later on, we'll find that this is convenient for us because we only have to add up from 0 to a, and then we can just simply double it. We're going to do that a lot, actually. So to summarize our three special function rules, we have the constant rule, which is really just integrating a rectangle. And then we have our special odd and even rules. If f of x is odd, then the integral from negative a to a of f of x will be 0. And if f of x is even, then the integral from negative a to a of f of x is twice the integral from 0 to a of f of x. Sadly, if f of x is neither odd nor even, then we can't say anything about the integral from negative a to a of f of x in general. Finally, I want to consider a couple of properties that we might call bounding properties. What we're going to do is to come up with a way to compare integrals to values here. And we saw one of these already. The first bounding property we can call the min-max property. And that is this. If f of x is trapped between a minimum value and a maximum value, then the integral of f of x from a to b is trapped between the area enclosed by the max and the area enclosed by the min. This property is actually really simple to prove. We can simply take this guy right here and integrate through. And here's the picture. I've got some f of x, and from a to b, it lies above m, little m, and it lies below big M. And so when I integrate from a to b, I get the net signed area here for f of x. But for little m, I get the net signed area right here, which is going to be the value of m times b minus a. And for the big M up here, I'm going to get the value of the area of that rectangle, which is again going to be big M times b minus a. And so the area of f of x has to be trapped between those two values. If we generalize that and say that f is bounded above by some function, g of x, then we can also say that the integral from a to b of f is going to be less than or equal to the integral from a to b of g. And the point here is once again to think of the integral in terms of Riemann sums. So if this is my f and this is my g, notice that my g actually drops below f over here, but that doesn't matter if I'm going to integrate from a to b. Since g is on top, then every single rectangle that I draw for f is going to correspond to a larger rectangle for g. And when I add up all those larger rectangles for G, I must get a larger area than I get for F. Those are the integral properties, and we're going to be using those to help simplify and, in some cases, find or estimate values for integrals. I want to close by just showing you an example of how we might use the min-max inequality to find some bounds on an integral. Consider an integral that might be difficult, in fact is difficult. The integral from 0 to 1 of 1 over 1 plus x cubed dx. So I look at this integral and I say, I don't know how to perform this integral, I don't know how to calculate its value. I can estimate it on the calculator, and that's perfectly fine. But I'd like to know something about the value of this integral. Then I consider that this function, 1 over 1 plus x cubed, has to have its largest value of 1 when x is equal to 0. And it has to decrease to a value of 1/2 when x is equal to 1. And it has to do that because 1 plus x cubed is going to get larger, and therefore 1 over 1 plus x cubed is going to get smaller as x increases. And so this means that this integral right here is going to be trapped between the minimum value of 1/2 times the width of the interval and the maximum value of 1 times the width of the interval. In other words, I can say that this integral is definitely between 1/2 and 1. Now those aren't very tight bounds, but it gives you a sense of how these min-max properties are used. I hope this was helpful to you, and I'll see you tomorrow.